Thank you very much, Ruth, and it is a pleasure to be here this morning. And as I got up a little early to make it up, the drive up from Hazle, East Lansing, and I was thinking the first Canadian origin air mass to make it into the Great Lakes. It's good timing, lake effect showers, to talk about climate change. But there was, I mentioned the Ruth, I saw sunrise near Cadillac on 115, and the indirect lighting from the side with the foliage turning was just glorious. There was a rainbow from a lake effect band, but it was just one of those things, a moment it's meant to be. So hopefully that's, what I do want to talk to about though today, climate change, as Ruth mentioned. I will be discussing, we'll start first with historical trends, then we'll look ahead with some projections, and as a third topic, something I think of special interest here and really elsewhere, and growing interest globally, and that is climate extremes, weather extremes, and the variability of climate, which is getting a lot of publicity lately. If there is one take-home message, or at least we'll say maybe one of a few or a handful, the first one is that while we as humans frequently think of climate as something stable or static, and in a human lifetime it is relatively static, or has been, it is anything but. Climate is a dynamic entity, and well, if you're close enough, you probably can't read all of the fine print here, but it's important to note that even here in Michigan, the climate has changed drastically in our past, especially looking at the geologic past. And we've had everything from a tropical climate 400 million years ago. That's actually the origin. Of course, we're in a part of the state where our state stone or rock, I can't remember the correct designation, the Petoskey. I always ask school kids about that. Do you find anything unusual about finding fossilized coral in the lake? And usually somebody said, well, isn't that a tropical species? And of course the answer is yes. It takes sea surface or sea temperatures in the mid-70s Fahrenheit or warmer to allow coral to grow or thrive. And that's indeed, at that point in time, geologic history, Michigan and the tectonic plate that it resides on, the North American plate, was much closer to the equator than it is now, and it's since drifted poleward. Now contrast that with about as recently as 12 to 15,000 years ago, and where we're sitting now was covered by a probably at least a mile thick sheet of ice in a glacial climate. And we've had everything in between. So one of the messages is again, as much as we like to think of climate as stable, it is truly a dynamic, changing system, and it undoubtedly will in the future. And what makes it interesting is that humans now very, very likely are having an additional influence. So we have both the natural part of this change as well as a human element as well. I'd like to start looking at the instrumental record. You're going to see several charts like this, and they tell a story. And I think the story is an interesting one because we're going to be looking at different variables like temperature and precipitation. And watch and pay attention because many of them are dynamically linked with one another. And it's a very, very interesting story I think they tell collectively. I'll start though with global temperatures. And this particular series record goes back to the late 19th century to 1880 and goes up through the last couple of years. And it basically is the best quality temperature records we have around the world, both on land and also on ocean surfaces, and how that's changed over time. And each of these particular points here is expressed as the difference between the global mean temperature that particular year and the a 100-year normal or long-term mean between 1901 and 2000. So it's a departure. If it's a positive number, it means that year was warmer than the long-term average, and vice versa if it's below. And what you can see here, the blue line that's here is a moving average, a 9-year moving average. It's meant to filter out some of the interannual variability and give us the longer, approximately decadal type of of changes or trends. It's very, very useful. You'll see several like this. And that's probably the most important thing to look at here in many ways, is what happens basically in that long-term trend. And what we have here is basically a world which is getting warmer. It's warmed on average a little bit about 1 degree Celsius, depending on how you define it or where you start. But that warming generally started here in the early 20th century, after the turn of last century, and has continued ever since. Now, with one exception, how many people have heard a little bit of controversy about the last few years, and that this rate of warming has slowed down? That's been in the media. Anybody? Here's some. Yes, many people have. And that's right here. This one, I believe this series goes through 2010. I need to update this, but you can see a leveling off of this, and so we're not warming as fast as we have in the past. And there's been a lot of research in this just in the last couple of years. And the likely answer to this, there's some probably good physical plausible reasons. It is not that the so-called greenhouse effect, the warming of the Earth because of this change in the atmosphere, that is still continuing. That energy, that additional energy that we get each year because of our changes in the atmosphere, that is continuing. What's changing is that additional energy appears to be going mostly into the oceans, into heating water. And of course, water is a great sink, an absorber of heat. And the latest estimates are that maybe as much as 90% of that additional warming or forcing of energy is going into the oceans. And so then the next question is, well, how long will that last before we see a resumption of the warming? And there's some debate about that, but some people think that it could be relatively short-lived. Others think it might be part of an ocean cycle, the Pacific Decadal Oscillation in the Pacific, of course the largest ocean, and that may cause this lapse to continue for several more years, or maybe a little bit longer. So it's something to watch. But if you have seen that and actually seen the leveling off here, that's at least probably the leading. Well, it's more of the theory. I think there's a lot of evidence to support that. But that's where that energy probably went. Now, in Michigan, what about locally here, or regionally, I should say? We have the first temperature records in Michigan that we know about historically came from Fort Mackinac and Fort Detroit back in the late the teens. 1819, I believe, is the first that I have seen. But those records were taken by the surgeon that was the surgeon that was attached to the local military, the Army unit. Some of those medical people did a great job at observing, others not so well. They were supposed to take observations 3 times a day. So we have some sporadic observations there, but we really don't have reliable long-term data until the middle of the 19th century in Michigan. This particular time series here starts in 1895 because of the number of stations that we have across the state. And what we've done is we've taken all of the data and averaged those together up through the present. And so in Michigan, each of the circles here, of course, is the mean average temperature that year, and then that thicker line is that moving average. And what you can see here, and this is true for much of the upper Midwest, we had a sideways trend back from the beginning of last century up to about the late 1930s. Then there was a general cooling trend of about 1 degree Fahrenheit until around 1980, and there has since been a 2 degree Fahrenheit warming on average. And you can see that there have been a couple very warm years. 2012 was, calendar-wise here in Michigan, was the warmest year that we have on record. But overall, our mean here, our running average, is still in the noise, but it's getting towards the upper part of the register, at least what we've seen historically. Now, the key part about this is this particular, especially last 3 decades, since 1980, is that it's not uniform, that increase or warming. Much of this, and we'll have to put a caveat here given last winter, but much of this warming has occurred during the winter season, especially December, January, February, and at night. So our nighttime minimum temperatures have risen, in some cases in the northern part of the state, as much as 10 degrees, just since 1980. And that even includes last winter, where we thought that the glaciers were just around the corner. So and I'll talk more about that in just a second. But very, very important to note that our summer temperatures, they've increased a little bit, but not nearly as much. Our spring temperatures are probably right after the winter. So it's not uniform across the year. Much of this, again, has been in the cold season. And speaking of last winter, well, I know most of you were here, and there are a lot of, we run out of superlatives to describe last winter. You probably have maybe even some four-letter type of words that you would use to describe last winter, but in a climatological sense, last winter was off the charts. And this particular graph also goes back to 1895, and the physical cause of last winter was basically a jet stream pattern across North America, which began way back before Thanksgiving last fall, and it continued. There was a break just before Christmas. There was another one right after New Year. There was one in February, but it continued all the way into March. That's something we rarely ever see. And of course, the pattern, I'm sure most of you could visualize that pattern, especially if you watch the weather every day. The jet stream was a huge trough over central and eastern North America with northerly flow right out of the Arctic, right down into the Midwest and to the east, and it just sat there. And typically, of course, the jet stream is continually changing, just like our climate. It's dynamic, it's changing, but we had here this basically stuck in one pattern. Now, if we look at the 5-month period, November through March, so 5-month period, that's what we're looking at, a trend here, all those together, and you can see that has been upward, definitely upward with time until last year. Here's last year. So for that 5-month period, it's off the bottom of the chart. You probably can't see it in the back. But it's referred to, some people in the atmospheric science community would call this just a singularity. It doesn't make any sense because there's nothing else close to it. It has been over 100 years since we've observed conditions like that or similar 5-month period. Got to go all the way back to the teens of last century. A long time, colder than the horrible winters in the 70s, and it just went on and on and on. Now, of course, with that, some of the impacts, long term, and by long term I'm thinking the last few decades, one of the other unmistakable trends associated with warmer winters, of course, we have less ice for less time on the Great Lakes until last year. This is the graph for that. This is taken from satellite, and it's basically an integrated area from satellite with time. This goes back to 1980. We only have reliable satellite we have satellite records since the early to mid 70s. That's when they started. But in terms, well, there are a couple things. We missed the all-time record. Anybody know what year the all-time record for ice on the Great Lakes? If you're old like me, 79. That's close. It was one of the really bad winters in the late 70s. We just missed it. In terms of total area, it turned out that, Superior was iced over, Huron was iced over, much of Michigan, there was only a little bit of open water. Erie, of course, always ices over when it's cold. It was Lake Ontario that was not cooperating and did not freeze, although if that's something we want. It certainly impacted shipping, and there were a number of other economic impacts. But we just missed the all-time record. So this year was the second most in terms of total ice area. But in terms of ice at the end of the season, especially in March, there's nothing on the record like it. We had more ice on the lakes this past spring than at any other time, at least probably in the last 50 years. Easily, probably have to go back to the early part of last century to have seen something like that. Of course, we don't have a reliable record. So the long-term trend is upward. Warmer winters, less ice, and of course the question is, well, what about this year? It probably is part of our natural variability. And again, one last thing about this is also, I think, very important to note, and that is while we shivered through a very difficult winter, you don't have to go very far. Remember the jet stream, ridges and troughs all the way around the hemisphere, and there were many areas of the world, as close as the western U.S. and Alaska, where the winter was abnormally mild. And Europe had its warmest or mildest winter in 200 years. Again, it's like the real estate adage, location. If that trough happens to be under you, there's really not much you can do about it. You're going to be stuck with that type of anomalous weather, or a ridge, the opposite, with mild weather. And it turned out that the winter, this boreal winter of last year, it was the 4th mildest on record, even with our, again, brutal conditions and polar vortex notwithstanding. So some interest, this is one of the, it's part of our natural variability. It's one of the reasons why that's so important to talk about. Now, there have been a number of impacts, and one of them is near and dear to most people here. We have gone since January of 2013 from a record low level in the Lake Huron, Michigan basin to almost back to normal. That's amazing. And if you look at the Corps of Engineers record, that's what this particular graph is. Here we are right now, and again, I'm thinking back here, if you can see around January of 2013, coming off, well, the drought year of 2012, at least in many parts of the basin. But we had an extraordinarily difficult winter with all sorts of ice cover that prevented evaporation during the cold season. But probably more importantly, we had much above normal precipitation over large parts of the basin for that time. And the result, look at the narrowing. Here's the normal here in the blue dash line. The red is the actual level, and you got a convergence of those two with time. You can see the seasonal cycles here. Typically, the lake reaches its maximum level during the summertime and its minimum in the late winter. That's typically how things work. But we're almost back to where we were. It's extraordinary to look at that. Just again, I became used to seeing the long beaches or the wide beaches and the plants growing out in areas that were formerly covered by water. Of course, now that's all reversed. And the outlook here from the Corps of Engineers for the next several months is to be fairly close to the normal. So that's a big change. And again, we owe that. If you look at the water in that basin, it's a balance between, on one side, the input, which is precip, and then the output, which is evaporation. So the two roughly balance one another out. There's a little bit of play due to humans and the Corps of Engineers and their locks, but most of it is about precip and evaporation, and certainly it has favored an increase in water lately. So that's a big change. One of the another important change to talk about also is linked to those milder winter temperatures. And we have seen some changes in seasonality. and there's some with some exclamation points in this part of the state. But this is a spaghetti diagram. It's a little bit busy. There are 3 series on here. And we have in green, this is the relative change of the date of the last freezing temperatures of the spring season from 1895 up through, about 2010. And in blue, we have the change of the date of the first freezing temperatures of the fall. And then in between, in red, is the period in between the last spring freeze, first fall freeze. So it's roughly our frost-free growing season in between those two. And what you can see with time, if you look at this, is that the last freeze of the spring has gotten earlier with time, especially in the last few decades. The first freezing temperatures of the fall have gotten later. And what we have in the middle is a longer frost-free growing season. And it averages out over the Great Lakes region to about a week and a half on average. We've done some research with this at MSU looking. In Michigan, it's not uniform. There's more change in the spring season. Our springs definitely are coming earlier than they have in the past. And of course, the exclamation point I mentioned here was 2012. I don't know if we have any fruit growers in the audience, but this was one of the most difficult or challenging years for our fruit industry in our state in its history. And in that year, we had a heat wave, an unprecedented heat wave in the month of March. And not only was it a heat wave for March, it was the greatest departure from normal, almost 14 degrees Fahrenheit on average in March of 2012. That's the largest departure of any month in our history. We've never had either cold or warm. We've never had one that far away. When you get climatologically, when you see a departure that reaches double digits, that's record-breaking. But not only did we go to double digits, we went even further than that. But that March was just incredible. And of course, the story after that, all that warmth, it melted all of our snow. It brought all of our perennial crops out of their protective dormant states. And then we went back to normal the last week of March and April. And of course, we lost almost all of our crops. So very, very difficult. If there's anything positive about that particular year, which was followed by a drought, ironically, in many parts of the state, it was that we now have federal crop insurance, which many fruit growers did not have access to previously. And that if there's any silver lining, that that would be it. And thank you to Senator Stabenow for that to happen, because it's something that's needed. Most of our major agricultural commodities have federal insurance or have an ability to try and protect themselves against some of the risk with weather and climate, but fruit growers did not. So that's a good thing. So our seasons are changing, and also, oh, here's, I should have looked at the next slide. This is, I mentioned 2012, and I've already told the story, but this one is some research actually I'm involved with right now. And this is for, if you can see down here in the bottom, this is the change, this is looking at the rate of development, growth and development of tart cherries. Of course, we're surrounded. This is it. This is the center of the world for tart cherry production. And on the vertical axis here, we have the day of the year. So day 70 would be the third week in April. Day 140 would be the third week in May. And it's for Traverse City. This goes back to the 1901 up through 2012. And this looks at the change in time in which tart cherries reach the so-called side green stage, which is down here in the lower left. And the reason this matters is because once cherries, after they come out of dormancy, break dormancy, they reach this stage, their ability to withstand cold is dramatically less than it would be if they were dormant or even before or coming out of dormancy. So here you've got a damage threshold probably in the mid-20s, 26 degrees Fahrenheit, something like that, but it's markedly different than what it is before. And typically this date in Traverse City has happened right around the end of April or beginning of May. But over time you can see that it gets earlier and earlier, and then there's even a greater change in 1980, and so now it's occurring fully a week and a half on average earlier than it did just a half a century ago. Here's 2012, again, off the charts. Not only did it reach side green, of course, we had bloom. That was also, and cherries have been grown commercially here in this area for a century and a half. It's part of the area's history and culture. That has never happened before, where bloom has occurred in March, but it did in 2012. So another again, a superlative to try and describe something very, very unusual, hopefully very, very rare and unusual. Now, there are also trends in terms of precipitation that are very, very important to talk about. And this is still the 1895 through 2013 time frame, and what we're looking at here is the annual precipitation, so all of the liquid and solid precip melted down and how that's changed. What you can see from the long-term average, the 1930s, like many parts of the Midwest and Central North America, benchmark driest decade on record. That was when it was driest, but ever since the 30s, with a couple of breaks here, it's been getting wetter with time. And so it's now on the order of 10 to 15% wetter on average than it was just a half a century ago. And that, for here, that translates to about maybe 4 inches of extra water we have now that we didn't before. And in contrast to what we describe for temperatures, or mean temperatures, this is much more uniform around the year. Summers are getting wetter, winters are getting wetter, spring. The only exception might be, to some extent, might be the fall. But most seasons are explaining part of this. Now, the next issue is, it's important to note, if we have more annual precip, there's 2 ways you can do that. One way is to have more wet days, and that is happening. This is a graph which depicts the ratio of measurable, or days with measurable precipitation each year. It's for a site in the thumb, in the east central part of the lower, but it's very representative. And the blue line here is that fraction or ratio of wet days. The green line here, both of these are increasing, but the green line here is multiple wet days events. So wet days which follow wet days. Both of those have increased significantly in the last, well, half century or so. There's a little bit of leveling off, but they're still relatively high. One way of looking at this, at least for measurable precip, is back in the 1930s, on average about 1 out of 4 days had measurable precip. Now it's more than 1 out of 3. So part of the increase that you're seeing in the last slide is due to more wet days. And, well, there's another part of that too we don't have as reliable data, but with more wet days we have more clouds. So there's been an increase. That may have leveled off recently, but long term it's cloudier now than it was in the past. Now, the other way to have more annual precipitation, of course, is to have more extreme events, or have more per event. And that's also true, or also happening. In the upper right here, this particular graph depicts the change in the sum of the 10 wettest days each year. So you take the 10 biggest events each year, you take their sum, and then you look at that sum over time. And the red dots here are increases in that sum. Blues are decreases. The size of the circle has to do with the statistical significance, how significant it is. But you can see over most of the Midwest, including Michigan, that number or that sum is increasing. And I think, well, so both of these things are happening. If you look at actually how much of that 4 inches of extra water, how much is one, how much is the other, well, it depends on location, but probably more of it, a little bit more of it is due to these heavy events. So they've also been on the upswing. Which brings me to the climate variability issue, and we talked about that and how important that is. Climate variability, extreme, and another take home, we talk about weather and climate. And they're very closely related, but there's a very important difference. Anybody know this? I start a lot of classes with this one. It's on exams. Weather and climate are looking at the same variables: temperature, pressure, precipitation, but they're looking at a different time frame. And weather, we talk about seconds, hours, maybe days. Climate, on the other hand, it's the same thing, but it's over multiple years, decades, centuries, or longer. So they're looking at the same variable, but it's different time frames. And we have to make the distinction. The heat wave of March 2012, that was a weather event. The winter of 2013, 2014, that's part of weather. It's part of the jet stream and the vagaries of that configuration. That's part of weather. However, over long periods of time, if we see repeated behavior and we see trends develop, then it becomes a climate issue. But the point here about the variability, climatic variability, and these extreme weather events, which are embedded in that in the short term, it's very, very important, because even though those events, and we're thinking about things like droughts, heavy rain events, hailstorms, hurricanes, all these are extreme weather events, even though they're uncommon or relatively rare, a small fraction of the total number, they're associated with a large part of the impacts that matter, both to us in our human systems as well as natural systems. So it's really, really important to understand or have a better understanding of these things. There's another piece here that is also very, very important, and that is that if you look at human history, and this is not the first time humans are faced with changes in climate. It's happened many, many times in human. If you look at the long-term history, it turns out if the changes in climate were relatively gradual over time, humans did a fairly decent job of adapting and coping with those changes, figuring out a way to make things work. Ultimately, if you look in the long term, something called habitat tracking, and humans, and this happened in the Middle East thousands of years ago. If things got really bad, the people basically just picked up, left, and went somewhere else to a more favorable location. Well, we really can't do that anymore, at least not in any easy way. So the variability, though, it's one thing to adjust to these changes in long-term steady changes. If we have changes in variability, again, the frequency of severe weather, the frequency of flooding, that's much, much more difficult to find or work out some engineered solution. Very, very difficult to do. And I've been at several meetings, and especially with the agricultural industry, and well, I'll give you an example. I was in Chicago a few years ago at one of these meetings, and they had a number of people from very large ag companies, the ones that really make the difference in terms of, well, they're industry leaders. And the idea was, the theme was climate change and technology. And the ag industry can point itself out as probably one of the premier industries, in terms of adjusting and coming up with new techniques to produce more food with less land, et cetera. They have a wonderful, an incredible track record in some ways in terms of productivity. And the question was, well, what do you make of this climate change? And almost without an exception, most of the people in the industry were very optimistic. We need glass half full people definitely in the world, but there was a lot of optimism. We can find a way. We will engineer a way out of these changes, and that went on. And there was a lot of patting on back type of things. And I raised my hand and I said, well, that's assuming that the changes might be orderly and steady. What happens if you get changes in variability? And it was crickets. Nobody wants to deal with that. And that's, well, I'm going to come to that. I want to finish up with this idea. And we really don't know. There's evidence on both sides here in terms of variability and changes. In some ways, the numbers of extremes in our region, they have increased. It's mostly due to the heavy rain events. But it's a huge wild card, and it's one that we need to be concerned about. I think I'm going to go on and not spend time with a statistics lesson here this morning. For all of you, I'll save you that. But this is the next chart here is an index that looks at the frequency of temperature and precipitation related extreme events for the Great Lakes region. And again, there's been an increase over the last several decades. Most of this is due to those heavy rain events that we saw. Not so much with temperature yet. We've actually seen, if you look at heat waves, actually cold waves as well, there really hasn't been much of a change in either for the last several decades. Most of this extreme type of conditions have been associated with precip, at least at this point. Other parts of the world, that's not true, but here in the Midwest, it's mostly heavy rain events. Which brings me to a very recent study. This is actually a study that was just published last week, this Monday, by the American Meteorological Society, looking back at the year 2013, and I believe it was about 12.5 extreme weather events that took place in that year around the world. 3 of them in the U.S. included the California drought, flooding in the Midwest, and then a blizzard up in the northern Great Plains. And essentially, they had weather and climate people looking at these to basically try to understand their historical relevance, and more a step further, can we attribute the occurrence of there was a lot of extremes. Is there anything we can attribute these to? Is it part of any kind of a longer term background change in climate, or is it part of this weather variability? Because remember, looking at these extreme events, it's very difficult. There's a lot of noise, a lot of variability from year to year, and it's really difficult to know whether these extreme things, are they just part of the noise, or is it part of a longer term trend? And that was the bottom line. And well, if I don't want to spoil it for you if you haven't read the study, but the bottom line is that several of these, I think maybe about 6, maybe it was 8, the number was, there was some evidence that these extreme events, and they included hurricanes, fires, there were some around the world, that about half of them appeared to be linked to some longer term background trend, which probably is linked with the warming of the planet, at least in some indirect way. Most of those in the U.S., the verdict was out, or they said no, this is just part of weather natural variability. And again, it's a difficult thing to say, so it depended. But the bottom line issue for these variable events is that even though this background change that is taking place in most of the world is relatively slow and not that much in magnitude, it raises the probability, not that much, but a little bit, that we do see these extreme events. And that's ultimately the concern over time, that some of these will become frequent enough to be a real problem that we have to deal with. The Intergovernmental Panel on Climate Change, the IPCC, which is an international group of scientists tasked with understanding climate and its physical processes, how it changes, how humans might be impacting it, and then what, if anything, can be done about it. They came out with some statements regarding extremes here, and at the top of the list here, looking ahead for the future, are increases in the frequency of warm temperature events. Now again, I mentioned we haven't seen that here yet, but in some parts of the world, Australia is one, they definitely have already seen increases. One of the interesting ones for us is down here at the bottom, and it's only, they note that there's confidence here. They go from virtual certainty, almost a given, to very likely, and then only medium confidence. So there's lessening a reduction in confidence as you go down. But the one at the bottom here is most relevant, I think, for us, and that's intensification of droughts. And that should always raise a flag in a humid climate, definitely, or in an arid climate for that matter. Decreases in the number of tropical cyclones, i.e. hurricanes in our side of the world, cyclones in other parts, typhoons in the Pacific, and the number of extratropical cyclones, fancy word for low pressure systems. Flags should go off there too, because where does a lot of our precipitation come from? Here in the Midwest. Certainly in the cold season, A lot of it is associated with those those low pressure systems as they migrate through the middle of the country. So a change in the frequency or the intensity would probably alter our climate in some way. And it's not clear. There's less confidence about this. I'll talk a little bit more about that in just a second. I want to leave you one more thing here regarding extreme events. And this is an interesting diagram. It's looking at the frequency or the change in $1 billion plus weather disasters around the world between 1980 and 2010. It's intriguing. The color bars here, the blue are insured losses that year, and then the oranges are uninsured losses. So it's collective. There are two types of disasters here that account for most of those. Anybody guess what those? You should guess probably the number one when you think about it. Hurricanes. Tropical cyclones are at the top of the list. The second one is not as what?
Fire.
It's not fire. They actually, and it is weather related, but they didn't include fires here because there are other factors too involved. Land use change, but it's another climate related disaster. Drought. That's good. That's really good. So tropical cyclones / hurricanes and droughts are the top two. You've got heavy flooding here on some. There's a couple big tornadoes that had more than $1 billion. But the bottom line is, if you look at this and you add it up, that number is increasing, or the number of these disasters, unfortunately, is decreasing with time. Now, here's the intriguing thing. If you look at the frequency of tropical cyclones and some of these other types of events, and you look, that hasn't changed that much. It's actually lower than it has been in the past. And yet, we see an increase in this damage. And if you're in the insurance industry, this is the kind of thing that keeps you up, probably late at night. But what accounts for the increase?
People living in those areas.
Exactly. There are more people. There's more of our stuff in the way. That's the way of looking at it. And so the conclusion is, and this has been, the insurance people, believe me, have spent a lot of time with this around the world, especially the reinsurance people who are responsible for the insurance people or bankrolling them. Our vulnerability has increased. Our vulnerability to these extreme events has unfortunately increased with time. That trend can't continue. We become too vulnerable. So an interesting thing to remember, it's not just about the changes in the events themselves, it's also relative to us and how particularly vulnerable we are. All right, let's look quickly here at a little bit of the future. Well, warmer and wetter has been the historical trend. It turns out that in general is the direction the projections for the future take us. This is a little bit difficult to tell. This is from the new 5th IPCC assessment report, was published last fall, or released last fall. And it's, well, I'll summarize here. If it's difficult to make a weather forecast for the next 36 hours or 48 hours, it's much more complicated to come up with a projection for the end of the century. But science has done it. There are about a couple dozen groups around the world that do this, and they use process-based physical models of the atmosphere and the oceans and the land surface and the interactions. Very, very difficult. And the models have become pretty good. 20, 30 years ago, they had major limitations. They still do in some ways. Clouds is one limitation, but they've gotten much better. They can do a good job of replicating our current climate. Who's going to believe anything that they can't do today? They could, and again, 30 years ago, they had a tough time. Now they can do that fairly well. So if you tell those models, let's look at our past, and then let's make some assumptions about the distant future. Again, you think weather and climate forecasting are bad. Think about economists have to be involved in this. They have to look at, and that's, we tease one another at who makes the worst forecast. It's economists. Everybody knows that. It's a just well-known thing. But they have to come up with scenarios: economic growth, per capita income, the demand for energy. There are a number of really social and other political issues that take place here. Another one is how much cooperation and collaboration do we have internationally? And of course, my opinion, not much. We could use a lot more. But what do you assume about that in the future? And so a number that it turned out that they came out with 4 major now scenarios of the future, and those range from business as usual. That's up here at the top. Basically, we don't do anything. And a lot of people in the lesser developed countries, the third world, who want energy and have every right to have if they have money to buy, they have power, and they use more energy per capita than they have. That's what happens, or at least projected to happen. That's the highest increase in mean global temperatures, and this is actually over North America. For Michigan here, we're looking at a change in temperature on the order of maybe 8 to 10 degrees Fahrenheit on average. That's huge, and it's especially huge in such a short period of time. So at least from we know, it doesn't sound like a lot, but over a period from 50 to 100 years, that's a big change. Now, contrast that with the one down on the bottom here. This is a scenario where the world somehow figures out a way to collaborate and constructively come up with, well, new technologies, greener or at least more energy conservation, and above all, they cooperate with one another, and somehow we engineer ourselves out some solutions. The warming with that one is more down in the maybe 3 degrees to 4 degrees Fahrenheit. So one take home here is that we are already committed likely to some additional warming in the future just based on what's happened over the last century to century and a half, really since the beginning of the Industrial Revolution. But a lot of the emissions have come in the last 50 years or so, and they're still, of course, increasing with time. So again, the bottom line is here, somewhere on the order maybe 3 to as much as 10 degrees Fahrenheit is what the simulations, our best educated guess of the future. And this is a graph, it simplifies something which is very complicated, but it's still an interesting illustration. How far do you have to go geographically now to find a climate that much warmer? And the answer is the lower Ohio Valley, possibly even down into the lower Mississippi Valley. And of course, all of us can appreciate things are very different there now than they are in the Great Lakes and in Michigan. But that gives you an idea, at least in terms of that magnitude, a change like that, and what that might mean. Think about our ecosystems and all of our climate-dependent systems. Projections also include, well, increases in the number of days above 95, further increases in our frost-free growing season. We're already seeing that now. But again, at some point, these projections say that the number of these extreme events is going to increase. We don't see that yet. What about precip? More complicated. Almost all, I don't think there's any exception of all of these projections of the future, and there are again more than a couple dozen of them, different flavors. They all say warming for our region. No exceptions. Precipitation is different, and some of the projections say that the Great Lakes region will become wetter. Some say drier. The majority say wetter, and that's probably the general direction. You can see globally here that most of the increases in precipitation, this is for 2 different seasons, but the most pronounced or profound changes in precip are at the high latitudes, especially the northern hemisphere, also the southern hemisphere, drying across much of the subtropics and tropical areas. That's a real problem in the area I work with food production. Those are areas which can little afford to become less productive, but that's unfortunately what the projection is. But Michigan is on the southern periphery of that area of increased precipitation, but there is a major caveat to that, and that is that if there are increases, these projections suggest that they occur in the cold season, in winter, and to a lesser extent spring, and more liquid precip than frozen. Our summers sort of level or flat, and of course, if temperatures increase anywhere close to what's being projected, the demand for water will increase, and we, of course, for our food production and our natural ecosystems, the water needs to be in phase with the warm season, and there's a lot of research occurring or going on with that theme right now. One last thing about the precipitation, and some of these projections. How many people have heard the statement that these projections say we're going to have both more heavy rain events and flooding and more droughts at the same time?
Yeah, no questions.
And the first time I heard Brian Williams or somebody talk about that after the IPCC report, I thought, wow. And I'll get to the moral of the story, but it seems completely counterintuitive, like an oxymoron. It doesn't make any sense. How can you have more flooding on one hand and more droughts on the other? And what they neglected, and what they should have said, it is possible. It is possible, even though we have more precip, and the physical mechanism, of course, most of you know the answer. It's that we have, even though there's more overall rain, it falls on fewer days. The key word there is erratic, that precipitation becomes more erratic with time. And that's I think whether you're talking about human systems or natural systems, that's a bad word. Erratic is not easy to adjust to. And so yes, maybe we have overall, but it means more extreme heavy events. It also means longer periods of time where we don't have precip, and then hence the potential increase in drought severity, and that's what this one talks about as well. Now, in fairness, this is one of the things that the models don't do as well. The projections don't do really that well with extremes. And I think the jury's still out on this, but it's really, really important that we have a better understanding, because those are the ones that the impacts are associated with. What about the lakes? We've seen already that Michigan Huron has responded very, very quickly to recent shifts in climate. Oh, 2013, by the way, and I didn't mention that, forgive me. 2013 was the wettest year on record in Michigan on the average, especially in western parts of the state and in parts of the UP. So part of that, again, that increase was due to the wettest year. If you looked at that series, 2013's alone, there's nothing for the last 100 plus years that wet on average. Well, 4 years ago, Catherine Hayhoe and colleagues came out with a study of the projected changes in Great Lakes level, and they collectively said basically we're going to see major decreases. This got a lot of publicity, a lot of press. It got everyone's attention because lake levels at that point were still really low, and everybody said, "Wow, that's." And we're talking here a couple feet, large changes. That's over here on the left. And well, it's looking at current time frame and then out through the end of the century here, but all of the lakes themselves, including Michigan Huron, were projected to decline. Now, the same year, Jim Angel and colleague Ken Kunkel in Illinois came out with another study, and they actually looked, it was a bit more comprehensive. They had more projections of the future, and they came up with a little bit more muted and neutral. Their results are here on the right-hand side, and they said yes, there might be some minor decreases, or there might be decreases, but they might not be, and there were even some increases here noted. And then finally, the year after that, Brent Lofgren and colleagues at the Great Lakes Environmental Research Lab came up with a new study with some new science, I think better technique, and they basically concluded that it could be neutral, that their changes were small, either way, increase or decrease. And so right now, sort of officially, that neutral is probably the leading candidate, and there's still a lot of uncertainty. So we can't say for sure, but again, the latest studies say not much change either way. But more, again, as usual, more needs to be done. Want to wrap up here and basically say, again, historically, warmer and wetter has been the direction. That's also the general direction for these projections in the future. Now, that could be coincidence, but I think it's important to note that they are in agreement with them, with each other. We could spend, well, if we had the whole day, we could talk about more impacts. It's also important to note that as the climate does whatever changes, that there are negative impacts. There are also positive impacts. Agriculture has benefited definitely from the changes of the last half century, without question, in Michigan. There are a number of other examples, but the change itself is the difficult thing. And somehow adjusting to those changes. And the issue of variability, can't put enough underlines about variability. It's one of the things that relatively less is known about. That's a really, really a big wild card that we need to know more about. And I will finish up with, it's a favorite image now. This is Memorial Day weekend, so last May. And this is taken at South Beach in downtown Marquette, looking out at Lake Superior. And you can see, basically, they're the first holiday weekend of the year. There are some hardy Yoopers out here on the beach, looking out at the ice flows that remained in Lake Superior, actually into June. There was still ice in the, but it's another an illustration, a reminder about that variability issue, how important it is. So I'll stop there. Do we have any time for questions? Yes, thank you very much.
Thank you. Can you speak to insect survival and the effect on trees and long term?
Question was, could I say or comment on the issue of insect survival or the whole pest complex. And I can't. I'm actually working on a project, the one involved with fruit. We have an element that looks at this. And the reality of it is it's one that we have very little understanding. But it is potentially a huge issue. And we have to, worldwide, it turns out that 40% of food production somehow never gets to humans. It's wasted or lost. A lot of it has to do with pests and diseases. But as, of course, if climate changes one way or the other, the risk of many of these types of diseases, and we have a number of examples in Michigan, Japanese beetle, those are exotics, or insect, Johnson grass is another one for a noxious weed, which has typically been confined to tropical areas and now is moving gradually north in the Corn Belt. It doesn't respond well to herbicide. There are a number of these examples, and they're there. Very little is known about. There's an ecological, a very, very important ecological question there, and we're just really beginning to investigate. And again, like the variability, I would say that is one of the real cutting-edge frontier topics that we need to, because it could potentially have as large an impact as some of these other things. So very, very important. We just don't know that much about it, but it could be really big. It already is in the western U.S. Looking at fire. Somebody mentioned fire. There's a insect and disease combination that goes and weakens trees and makes them more susceptible to fire. These things are all linked dynamically together, but it goes back to the risk of the pest and the disease to begin with. Yes, ma'am.
Johnson grass, is that what?
Johnson grass, yes.
It's a big problem just on farms.
As
My
a
daughter
small
farms and she's
question,
having a terrible
I'm
time.
following what you said about precipitation, more extreme events. And I'm really aware that the Ogallala Aquifer had all of that water underground for all of that time, and our irrigation has pulled that up. It's almost, it can't renew itself anymore. That's a separate question. Is it possible that by taking water that had been stored underground and bringing it up into the atmosphere, that's intensified this wetter climate change?
That's a very, very interesting question. Actually, one of my colleagues has done a study on that, and the question relates to the massive amount of irrigation we have out in the Great Plains, especially the high plains that are using groundwater, actually fossil water from the Ogallala Aquifer and other, but Ogallala is the number one, and essentially taking out that water at a much higher rate than any replacement. And it's water that's accumulated over thousands of years. And the issue is, to one of your questions, is we can see now there is some impact of massive irrigation. We can see a little bit of an increase in the frequency of rainfall and a little bit heavier rainfall in the vicinity. So most of that moisture is recycled locally in showers and thunderstorms, but it's not much. But in a longer term sense, it's just not sustainable. And unfortunately, for some of the ag industry, especially the animal industry, feedlots that rely on irrigation for feed, for corn in the Great Plains, it's becoming more and more expensive to produce the corn for the feed. And again, given that it is not sustainable over time, this is a real problem or challenge. There may have to be some relocation of that industry at some point. There just is not enough water. The other follow-up on that, and you probably noticed from some of these maps, if we look at so-called winners and losers in these projected changes, we're in a part of the U.S. in the Great Lakes where some of the changes would be at least less adverse or maybe a little bit more simpler to deal with. In parts of the southern and western U.S., especially from the southern Great Plains westward over to the southwest, there it's a much more challenging. All of them are warmer and drier. They already have problems now, and they're likely to get worse, at least with these scenarios. So in that sense, relative-wise, we're here in this region a little bit better than others, or could be potentially. Yes, sir.
Well, certainly last winter I had fun saying, in Michigan, would a couple degrees warmer really be so bad? I understand, yes it is. But my question really is, do you have any further comments as to why 2012 and 2013 were such anomalies? Is there any further speculation on that? Or just part of a varying trend?
The question was, we have witnessed and observed and experienced, in some cases too much experience, some extremely variable conditions over the last couple of years. Is there some kind of a trend there, or or is it just part of the natural variability? And this would be my opinion. I think most of it is still in that noise, is that interannual variability. It's just there's a lot of variability. It's difficult to attribute those, I think, to any longer term change. It could be, if it is, it's probably a very, very minor contribution. I think most of what we're seeing is some of that variability, which we're stuck with. It just happened to be larger over the last couple of years. That's the answer right now. Of course, if we see repeated behavior, we'll have to revise that, I think.
Okay, one last question. I'll make it two. Okay,
Yes.
two more questions.
You spoke to averages over 10 years.
Yes.
Technically, is there going to be any change in using 10 years? Because it seems to me, if you're talking about long-term trends like such as climate change,
Right.
if you keep moving your 10 years, you're not going to see variability. Is there any, I'm assuming that 10 years is pretty much the standard. Is there talk about extending that to 20 years, 25, and so on, given that you will then have, assuming consistent data to work with?
That is a wonderful question, and you'll be surprised at the answer, because the International Convention for Climate, quote, normals, it's 30 years, and that was decided several decades ago, and it has to do with the human lifetime, in essence, what we as humans look at this. So the 30-year period, at the beginning of every decade, we use that 30-year period. But your point is very, very well taken, and it's exactly right. There's an argument now that 30 years is too long, because if we look at our normals, we're shooting at a moving target, and it was cooler, especially the winters were cooler 30 years ago than they are on average now. So you need to have something in the middle of the road. So there have been proposals to reduce the number, and some of the people who work in this in the insurance industry, they're working on 5 to 10 year or less. So they have shortened up their time horizon a lot, because they acknowledge, yes, we are working with a moving target, but so we're still stuck officially at 30, but it probably will be reduced in the future.
Okay, Mary Lee.
This may not be a weather-related question, but I'm curious to know what you think about the effect of GMOs on the pest problem.
A tough one, and I probably would have to. I have colleagues who work in this. The question was about the effect of GMOs and how that relates to some of the pest issues that we talked about. And I work with the agriculture sector a lot. It's a complicated problem, because on one hand, GMOs unquestionably have increased productivity. There's no way we can. It just happened, and we're producing more with fewer resources and less. But there also, on the other hand, there's a potential for ecological experiments, or for something to get out of hand. The Europeans, by and large, still they're not legal to have GMOs in many parts of Europe. The US has looked at this differently. I don't know that we're going to come up with a solution. I think there's word that Europe might actually accept some types of GMOs, but it's going to have to be under special circumstances. So I guess my uneducated view of this would be that we probably still have to look at the technology, but somehow we have to make sure that it's safe. Because if you make a mistake, and there have been many mistakes made, of course, over time, we can't just go and grab it back. It would be difficult to go back. So it's definitely, though, for our future. There's no question it's a part of the future. It has to be a future discussion, because as the population grows, it's going to be difficult to keep up with the demand for food.
Sorry, we're going to have to cut the questions off there. I would like to thank you so much for coming up,
you're
especially
welcome.
under difficult circumstances.